Hello, chemists. This is Ms. Placino, and you're watching lesson 11.5 on shifting equilibrium. In today's lesson, we're going to talk about what happens to an equilibrium system when we stress it. Goals for today's lesson. You should be able to identify the different ways to stress a system that's at equilibrium. And the big one today is predicting how that equilibrium system is going to respond to the stress and explain why this occurs. This is a super important lesson in this unit, so really make sure you're kind of paying full attention as we go through this information. Let's get started. All right, so we're going to study this reversible reaction with hydrogen and nitrogen in a reversible reaction with ammonia. We're looking at a graph of concentration versus time. How do we know that this system has established equilibrium? Hopefully you're taking a look at the concentrations of the three substances. You're noticing that they're remaining constant, and that is a good indication that equilibrium has been established. So concentrations are constant. That means our forward and reverse reactions must be occurring at the same rate. We're now going to stress this system that has established equilibrium, and in order to do that, we're going to put more H2 into the system. In other words, we're going to increase the concentration of hydrogen gas. So what might that look like on the graph? Hopefully you're thinking, well, maybe we see a spike or an increase in concentration of H2. And sure enough, that's what's going on in this kind of, like off-white shaded part of the graph. We see that increase in H2 concentration, and then as a result of changing that, you can see that we are also going to impact the concentration of ammonia, NH3, and nitrogen gas. So let's talk a little bit more about this. Once we add in the H2, we see changes in the concentration of all of the substances. We can see once the H2 is added, its concentration starts to decrease. The concentration of ammonia over on the product side starts to increase, and nitrogen, the other reactant, also starts to decrease. So this is how our system is responding to the stress of adding additional hydrogen gas. We decrease the concentration of H2 and N2, and we're increasing the concentration of our product, NH3. At a certain point in time, the concentrations will stop changing, and they will kind of level out again and remain constant. That's telling us that equilibrium has been reestablished. Notice that we are at a different equilibrium position. In other words, our new equilibrium, we've got different concentrations of H2, NH3, and N2 than we had before stressing the system by adding H2. What we're really going to be paying attention today is what's going on in this kind of like off-white area. Once we stress a system, how is it immediately going to respond in an attempt to reestablish that equilibrium? So this concept that we're going to be studying today is called Le Chatelier's principle. And kind of our unofficial mascot for this concept is a seesaw. I'm sure you know from your vast life experience that at a seesaw, one side goes up, the other side goes down. And I kind of want you to keep this picture in your head as we're talking about different ways to stress the system and how it will respond. So again, think of an equilibrium system as a seesaw. As one side goes up, the other goes down. So if we have an increase in the concentration of the reactants, the products have to experience a decrease. Anytime we stress the system is going to try to alleviate that stress by doing the opposite. For example, we stressed the system in the previous slide by adding additional H2. The system responded by trying to get rid of that H2. As the reactant side increases in concentration, we know the product side has to decrease in concentration and vice versa. You can't have both ends of the seesaw going up or both ends going down at the same time. If we're looking at a system that's got multiple reactants, like we just saw, if one reactant decreases in concentration, everything on the reactant side has to decrease in concentration as well. You can't have, one part of the seesaw going up, the other on the same side going down at the same time. It just does not work that way. And finally, we're going to look at how the system responds immediately after you stress it. So now where will the new equilibrium points be? But I've caused the stress. What is happening as the system tries to reestablish equilibrium? All right, let's take a look at some examples. I'm going to keep looking at the system that we saw in the previous slides. We're looking at a reversible reaction between hydrogen and nitrogen to form ammonia, and this process is exothermic in the forward reaction. In other words, it produces heat. So what we're going to visualize is our system looks something like this. We've got a closed container with hydrogen and nitrogen. H2 is these little white diatomics, N2 the blue diatomics, and ammonia, of course, are these molecules. They're all in the same container. We're going to look at a potential energy diagram for this system. Our reactants, hydrogen and nitrogen, have greater potential energy than our products. Okay. So let's talk about changes in concentration. And we've kind of already taken a look at this with the graph at the beginning of the presentation. If we add H2, so we've thrown more hydrogen in the system, how does the system respond? Well, we know the system wants to do the opposite. So the opposite of adding H2 is removing H2. Of course, the system can't somehow open itself up and round up some of the hydrogen molecules and kick them out. What's the only way to decrease the concentration of H2? It's by reacting it with N2 to produce more NH3 that will use up the H2. So we'd see a decrease in the concentration of hydrogen and nitrogen gas, and we'll see an increase in the concentration of ammonia. So in this case, we would say the equilibrium has shifted to the right, meaning the materials to the right of the arrow, in this case the product side, experience an increase in concentration. We would say that the forward reaction is favored. Two different ways of describing the shift. We've got the forward reaction favored because that's the one that's picking up speed. We're seeing an increase in the number of collisions between hydrogen and nitrogen, so we're producing more of our ammonia. If we add more N2, we would see the same exact change occur. We have more nitrogens present, so there's better chances of hydrogen and nitrogen colliding to form ammonia. So again, we'd say that the equilibrium has shifted to the right and that the forward reaction was favored because we see an increase in the concentration of the product. What if we add more NH3? The system is going to respond by trying to get rid of the NH3. The only way to do that is to decompose it, produce hydrogen and nitrogen gas. So hopefully you're predicting we'll see an increase in the concentration of our two reactants, a decrease in the concentration of ammonia. So in this case, we would say equilibrium has shifted to the left. The reverse reaction has been favored because our reactant side has experienced an increase in concentration. Another stress that we can put upon the system is to try to decrease the concentration of some of the substances. Let's say we remove some H2 from the system. Gotten rid of a couple of them. Now it's less likely that collisions will occur between hydrogen and nitrogen, and it's become more statistically probable that collisions will occur between NH3 molecules. If we remove some hydrogen, the system will respond by trying to replace it. The way to replace it is through the reverse reaction. So the system will immediately respond by lowering the concentration of NH3. It will react to produce H2 and N2. We'd say the equilibrium has shifted to the left and that the reverse reaction was favored. Go ahead and make predictions for removing N2 and also removing NH3. If we remove N2, it should be the same net result as when we remove hydrogen. We'll see an increase in those concentrations because ammonia is more likely to hit another ammonia molecule and that decomposition reaction to occur. We'd say equilibrium shifts to the left and the reverse reaction has been favored. If we remove NH3, the opposite is going to hold true. We'll have more likely collisions between hydrogen and nitrogen to produce ammonia. So we'll see an increase in the ammonia concentration, a decrease in the concentration of our reactants. We'd say equilibrium has shifted to the right, and the forward reaction has been favored. For most of our equilibrium systems, we're going to be studying gas systems only, so they're going to be very, very sensitive to changes in pressure. If we increase the pressure on the system, you can kind of imagine just decreasing the volume. So let's say we just kind of squish all of those particles into a smaller space. When that occurs, we have less volume. the system is going to respond in a way to give itself more space, or essentially more volume. So we want to pay attention to number of moles of gas on the reactant side and on the product side of this equation. So I've got a total of 3 plus 1 moles of gas on the reactant side, so I've got 4 moles. And on the product side, I just have 2 moles of gas. If I increase the pressure, I'm going to favor the side that has fewer moles of gas. I will see a decrease in the concentration of hydrogen and nitrogen, and I will see an increase in the concentration of NH3. So again, we'd say this stress shifts the equilibrium to the right, and our forward reaction has been favored because we see that increase in the concentration of the product. If we do the opposite, if we decrease the pressure, we kind of give the molecules more space, if you will, they will try to take up that space. We'd see the opposite. Hydrogen and nitrogen, the side with more moles of gas, will experience an increase in concentration. The ammonia side will experience a decrease in concentration. In this case, equilibrium has shifted to the left, and the reverse reaction has been favored. A system that has established equilibrium can also be stressed by changing the temperature. So we've got to pay attention in this case to where the heat term is. Let's say we increase the temperature. You can almost think about heat as being kind of like in this case, a product. I've added heat. So in a sense, I've increased the concentration of heat. The system is going to want to respond to use up that additional heat. It's going to favor the endothermic reaction, which in this case is the reverse reaction. So if I increase the temperature, I should see an increase in the concentration of H2 and N2, and I should see a decrease in the concentration of ammonia. Equilibrium has shifted to the left. We favor the reverse reaction. You can probably imagine that the opposite holds true if you decrease the temperature. Let's think about why that is. If I decrease the temperature, the opposite of decreasing the temperature is, of course, increasing it. The system is going to want to effectively warm itself up. It's going to want to produce heat. So in this case, we'd favor the exothermic reaction. We'll see a decrease in the concentration of N2 and H2 and an increase in the concentration of NH3. The reaction is shifted to the right, and the forward reaction has been favored. You can kind of think about it, if it's hot or cold out, how you would feel about somebody bringing like a heat source into your area. If it's hot and somebody brings like a heater into the space that you're hanging out in, you're probably going to want to get away from the heat. So you'd run away from it. If it's really cold and somebody brings a space heater into the room you're hanging out in, you're probably going to move towards the heat so you can warm up. So if you cool off the system, go towards the heat. It's kind of another way of thinking about it. All right, so those are the 3 big ways to change or to stress a system. You can change the concentration, either by increasing or decreasing concentration. You can change the pressure. Again, we're going to be looking primarily at gaseous systems, so they're going to respond to changes in pressure. And you can change the temperature. Those are the ways that you are really going to see the equilibrium shifting. There are a couple of additional stresses that I want to talk about. Let's talk about addition of an inert gas. You might remember that inert means non-reactive. So we're looking primarily at group 18 elements, the noble gases. Let's say you go through and you add neon. Throw a bunch of neon atoms in there. What impact do you think that might have? Well, it doesn't really react with anything. It actually doesn't cause any shift in equilibrium. What happens is you have changed the partial pressures of all of the substances in the mixture, but they've all changed by the same proportion, so you don't see any shift. So if I add an inert gas, I don't expect to see the equilibrium moving at all, and neither reaction is going to be favored. It does not matter which inert gas you add. What about adding a catalyst? Will that shift our equilibrium? And I know a couple of lessons ago we talked about what happens in our potential energy diagram when a catalyst is added. Hopefully remember that it looks something like this. We've provided an alternative path with lower activation energy. If there's less activation energy, what do you think is going to happen to the speed of our forward reaction? Lower activation energy, going to go faster. But what's going to happen to the speed of our reverse reaction? Oh, it's got lower activation energy as well, so it'll speed up too. Adding a catalyst, much like adding an inert gas, has no impact on the equilibrium. It will not shift it, and we will not favor either reaction. So adding an inert gas, adding a catalyst, no shift. All right. And finally, just to wrap up, I want to talk about something called the common ion effect, which is really just a kind of another application of Chatelier's law, looking at changes in concentration. So we've been looking at gaseous system. Common ion effect applies to aqueous systems. We've got sodium chloride, solid, we're saturated, so we've got sodium and chloride ions in a reversible reaction. If I start to add some BaCl2, some barium chloride, effectively, which of these substances have I increased the concentration of? Hopefully you're thinking, oh wait, I see Cl. I know barium chloride breaks apart. I'm going to be making barium 2+ ions and 2 chloride- ions. So effectively, I'm increasing the concentration of chloride. I'm going to try to decrease the concentration of the chloride ion, so that would probably cause the equilibrium to shift to the left and favor the reverse reaction. And that is exactly what you'd see. What if I had something that has a cation in common? Same idea. I'm going to increase the concentration of the sodium ion. I will force the equilibrium to shift to the left and favor the reverse reaction again. So just kind of the takeaway from the common ion effect is adding an ion will cause the system to shift towards the solid every single time, as long as the ions are on the product side. All right, that kind of wraps it up for today. This is definitely a concept that you're going to want to practice with. You've got tons of practice problems available to you in your workbook, so just try it out, keep practicing, and always just think, okay, what is the opposite of the stress I'm placing upon the system, and how is the system going to achieve that? Will it favor the forward or the reverse reaction? Good job today, chemists. Thanks for tuning in, and I hope you found this helpful.